So we continue this afternoon session with Marcio. Marcio finished his PhD in Uppsala. He had his postdoc in UC Irvine. And Rafael and I were very happy that he accepted the invitation. He looked for people in Brazil that we wanted to invite. Marcio reacted quickly. Others, he didn't reply.
They were in vacation.
I don't know. I think they were in vacations or something.
December's vacations, yeah.
Exactly. And then some of them 2 weeks later, it's, oh, well, too late. But so I'm very happy that Marcio accepted. Marcio, he's telling us about the spin and orbital Hall effects in 2D topological materials. Marcio, thanks.
Thank you very much. Thank you, Rafael, for the invitation. It's a pleasure to come back to Miami and to meet here at the Institute, and also to have these different talks on math. And I was telling that my daughter likes math very much, and I told her that I was going to meet a lot of mathematicians. And she asked me, how was the meeting with mathematicians? I said, oh. I didn't understand a lot, but she said, okay, tell me something. You know, start throwing names, and said, yeah, that's hard. Yeah, but she's very excited about the math. So maybe in a couple of years she will be around. So I'm going to talk about the spin and orbital Hall effect in these 2D materials, topological materials and also non-topological. And I come from Fluminense Federal University in Rio. Actually, we are in the state of Rio, but not in the city of Rio. We are across the bay, which is much better because then we have the view of the Rio. And we say that people are not from Niterói, that's the city. The best thing of Niterói is the view, so they hated us for that. And the view is, I'm going to show you here some of the pictures of the windows of the Institute. You can see the sugar loaf, and then you can see all these nice landscape. Of course, none of that applies to me because I'm a junior faculty, so I have a shaft. My window faces, of course,
Toilets.
So none of that applies. But anyway, the view of the campus is very nice, and then we have a good infrastructure in the few recent years.
This is the red beach, right? Just to the left from the
Praia Vermelha, yeah. So you know you are. That's true. The other side is Praia Vermelha, red beach. Yeah. And but this is just I'm going to pass a little bit fast the list of my collaborators. I didn't have the pictures of these other guys, but put only the professors, the other ones. And then most of this work have been done with this group here, and we have from my university now. I'm working with Professor Roberto, Antonio, and then Professor Nardelli, that's here from UNT, and my former postdoc supervisor, Roberto Fazio, and Tatiana, that's also from Rio, but now she's spending some time in, Tatiana and Antonio, they're spending some time in Portugal, and Jagoda is from Netherlands. And these are my colleagues at the time, they are postdocs and students, and now everybody moved on. Probably these affiliations here are wrong already. But anyway, I have a lot of have to thank these guys a lot because we did many things, a lot of implementations, a lot of things that unless we had this large group would be very difficult to do it. So this is the outline of my talk. I'll give a brief introduction of what we are doing. I'm going to talk about these Hall effects, which during the week have been talked a lot, but anyway, I'm going to engage in a couple of slides talking about them. And then I'm going to say what we have been doing, and then I'm going to engage in some shameless advertisement for our code. You know, we have been developing this code for the last few years, and it's, how can I say that's very good code. And then we go to the topological materials. In the end, I have one slide that we are doing this materials informatics, machine learning, and all of that on top of these things. Okay, so traditionally, what have been done in the last 50 years, we are having building devices and applications manipulating the electrons charge. You know, so we have come so far using this type of materials. But anyway, the electron has all the degrees of freedom. An intrinsic one, that's its spin, and it can acquire an orbital degree of freedom when it goes through the lattice. What I'm going to show in the next few slides is how we can connect all these different degrees of freedom and how we can take advantage of these degrees of freedom for applications and all. And then I'm going to show that some of these phenomena can be connected to this topological phase. Okay, so the first that I'm going to show is the ordinary Hall effect, where you apply an electrical field in this longitudinal direction, magnetic field in a perpendicular direction, and then you see these charge accumulations in the side of the sample. So this is kind of, we have been seeing this popping up during the week. And it's something that's interesting, that if you ever read the original Hall paper it's like when you go through your life, you learn things of people. And I learned with my former postdoc supervisor that you should always read the original papers. And then when you read the original paper, Hall starts the paper by saying that Maxwell was wrong. So he started the paper saying that. And it's very interesting because he was wrong, and of course, in this particular case. And then if you have time, go back and read the paper. It's very nice. So in this particular case, we need to apply electrical field to see this charge accumulating the sides. We have to break time reversal symmetry. And for 2D materials, if we have a stronger magnetic field, then depending on the sample, you can see this quantized version of this Hall effect. Okay. And then after this, the ordinary Hall effect, the Hall itself managed to measure the anomalous Hall effect, where you didn't have this magnetic field, was not necessary because you had a magnetic material. And following that, I'm going to show a timeline in a few slides. Several other different Hall effects have been proposed. And another one is what we call the spin Hall effect. The setup is quite similar, but with the exception that I don't need magnetic field, and I apply electric the flow of a charge current along the longitudinal direction is going to result in accumulation of spins in both sides of the sample. In the previous case, it was accumulation of charge. Here is going to be accumulation of spin. And this can be, this was proposed in the 80s, I'm not sure, 80s or 70s, in the end of the 70s. And this was observed via these Moog measurements in the samples, where you see that the spin up is accumulating spin up in one side and the spin down in the other side. Okay, so this is the signature that of the spin Hall effect, and this is going to be important for a small part that I'm going to mention in the few slides. So right now we can connect the charge with the spin, because now this is a charge flowing, and then I have a flow of spin in the perpendicular direction. And more recently, again, there are several flavors of Hall effects: phononic Hall effects, magnonic Hall effects, and this is what we call orbital Hall effect, because when the electron travels through the lattice, it can acquire this orbital character that depends on the system that you are. And what's interesting that I didn't mention before, the spin Hall effect, you need to have a material with strong spin coupling, so you can have this one. For the orbital Hall effect, this is not necessarily the case. We can have the orbital Hall effect is going to be, we apply electric current along the longitudinal direction, and we're going to see accumulation of different orbital characters in the side of in the letter of the sample. Okay, so we can have a multi-orbital systems, and these have been mostly studied in metals, and does not depend on the spin of the coupling. What's going to depend on is the crystal symmetry of the lattice. And this was predicted in this bismuthine on silicon carbide and some other TMDs that they had. Actually, these papers are from some of my collaborators. Okay, so this now with this, I have a different. The idea is the following: we have the lattice that's going to give you a orbital character depending on the arrangement of these atoms, and then the spin of the coupling is going to couple this spin to the lattice. And then we are going to have this orbital character being acquired via the lattice when the spin travels through. So now that we have this orbital Hall effect, we can connect the spin to the orbital degrees of freedom. So I can now close my system, because to induce the orbital Hall effect, I have to pass a charge longitudinally, is going to connect to the orbital degrees of freedom, and also via this mechanism here, I can connect also the two spin and orbital characters of this phenomenon. Okay, so and in general, you can this picture here is kind of when you don't have any electrical field applied, you can see that this system is going to be in this how can I say, this circle here where the orbitals are represented by these green and red points here, and it's in general for most of the materials you have this so-called quenching of the orbital moment. When you calculate the average of the orbital moment, it's going to be 0. But anyway, when you apply electrical field, you can, how can I say, this firm surface is going to be dislocated, and now we can have this orbital. The average of the orbital moment is going to be different of 0, simply because now you can shift the firm surface a little bit by this electrical field. Yeah, this picture is very, if you go to the Kittel solid state book, you're going to see something very similar, but not for orbital resolve with the firm surface, but just for the regular firm surface, okay? And then what we have now is that these Hall effects connect all these degrees of freedom, and we can now play with these different ones to get the response or whatever we like it, okay? So at this point, I'm going to switch a little bit, just the timeline of these phenomena. The orbital Hall started in 2005, around 2005. It was dormant for several years, and then, I don't know, a couple of years ago, it started getting momentum again. And now I'm going to show that to experimentally observe the orbital Hall effect is very difficult because you cannot never separate them from other effects. But the people have been doing these with different setups. I'm going to mention when I get there. Okay. So now I'm going to switch a little bit because most of what I do is these DFT calculations. But to do the kind of DFT calculations that I have been doing the last few years, I needed to get to this different framework, because otherwise it was going to be too costly, computationally speaking. So now I'm going to talk a little bit about this kind of calculations that we have been doing, like this. We have been performing high throughput calculations to search for new materials. So we start from these databases. Constructing the database is a very difficult problem, not difficult, but time consuming. So we are using the database that we already have. And then for some problem, we decided these criteria to filter the materials, because in general, this database, they have hundreds and thousands of materials. It's impossible to run all of them. After we filter this information, we go to the DFT calculations, and then in the end, we get the selected material that we like. So this is a table of, it's already a little bit outdated. This is from 2019, and out of these several databases, I'm going to use on this work here, the C2DB database. The database is from the Danish group of Professor Tigesen, and I'm going to comment a little bit in the next slide. So what these guys did was the following. They performed massively DFT calculations to predict the new 2D materials, but they didn't came out of nowhere. What they did was they got they went through the literature and saw which materials have been already synthesized. Graphene, molybdenum disulfide, and iron, germanium, tellurium, whatever kind of structure you have it. And then they started making chemical substitutions, and then calculating the DFT calculations, performing the DFT calculations with these new chemical formulas, and they have been publicly in these C2DB databases. And what's interesting that they have also some kind of stability criteria. I'm not going to go into much details. I can, if you guys like, you can go to this paper. It's very nice. So what's also nice is that the usage of the C2DB is very good. I wrote it to Professor Tigesen. He just sent me the database, and I could use it very easily. So that's why we decided to go with the C2DB, and also we are interested in 2D materials as well. So now with this, this is a sad story that I'm going to say here, because with this database, I databases that there was at the time around 4,000 materials. I wanted to check it for topological insulators, quantity spin Hall insulators. So I eliminated, I selected only for insulators, I eliminated all the magnetic materials, and I end up with 743 materials, but I didn't want to investigate the low stability ones, you know, positive formation energies and phonons, negative, imaginary phonons. So I used only the high and medium stabilities that they had. So I end up with these 700 materials, and I calculated the Z2 for all of them. And I found the 30 quantity spin Hall insulators. I'm going to tell how we did this, because this was not done this was done with our code, the Paul flow code that I'm going to mention. And we are about to write this paper, but then Professor Chigson put out his paper classifying the databases completely. You know? So just like, of course, his paper is much better than ours, because he also did the Z2 and also the mirror chain number calculation. So topological insulators and topological crystalline insulators. And at this point to say, okay, what we do with all these 700 insulators that now I'm going to mention in the next few slides. I have these 700 DFT calculations. Yes.
Oh, sorry to interrupt. I just wanted to ask, in these crystalline phases that they did in this paper, they only consider mirror chain number, or they consider other?
No, just mirror chain numbers. Because it's like what we are thinking about the rotational symmetries and.
Yeah, like other crystalline.
Yeah, because the problem is that for example, if you want to reproduce these results of, there is no automatic code to have these mirror chain numbers, at least not as far as I know. So this is an in-house implementation that they have. Probably the rotational ones would be trickier to do the calculation automatically at the time. I don't know. And this was lucky for us, because then we could do something on top of this. Otherwise, it's
okay, that's right. Yeah.
But now we did these calculations, the DFT calculations, but to calculate the Z2, I have integrated our code, Paul Flow, to the Z2 pack. That's one of the best codes to run these calculations, okay? So in the next few slides, I'm going to, again, go through this shameless advertisement of what we have been doing with the code. And because this is important, when you're doing high throughput calculations, of course, you want to do it the most efficient way you can. And our method is going to show to be very efficient in this way. Okay? So what we want to calculate is the spin or orbital Hall conductivity that's given by this expression that you guys have been seeing this expression the whole week. And then in the end, if we have, this is the current operator. If we have the spin operator here, we're going to have the spin current, and then we're going to have the spin Hall conductivity. If we put the orbital operator, we're going to have the orbital current and the orbital Hall conductivity. And the biggest problem here is this region that we have an integration over the Brillouin zone. You have a sum over the bands. And of course, this integration, if you ever run these calculations, is going to be in the region of hundreds of thousands of points that you need to integrate. And the number of bands depend on the system that you have. But if you're running DFT, this number of bands, they become very large, very easily. So this is very costly to do it. People do pure ab initio, pure DFT. But in general, when you look at people have been doing this is in these localized bases, like LMTO, KKR, people from UD to do it. And there is also some other groups that use these localized bases for calculating these quantities. So right now, what we are going to do is the following. I'm going to perform these integrations in the fastest way that I can, saving memory, saving time, whatever I can to make it faster. So if you know anything about the DFT, there are several flavors of DFT. You can do DFT with localized bases. You can do DFT with LMTO, whatever kind of bases you like, Gaussian bases. But the most, how can I say, common codes that we have been using is these plane wave bases. Ponto Expresso, VASP, these are all plane wave block states bases. And going from, and you can use these also localized bases, atomic orbitals. Going from right to the left is easy. Just take a Fourier transformation. You go from this localized picture to the localized block states. But going from the left to the right, that's a problem. Because now we have this completely delocalized basis all over the place. If you have a 2D material, for example, the materials in general, what we do, we have a periodic boundary conditions everywhere, but in the perpendicular direction, you don't have material except in the middle of the box, let's say. But in any case, you have plane waves occupying the whole region, even if there is no material in that region. So to go from left to the right, you need to do something different. The most traditional way that people have been doing this, using Vernier 90, the Vernier method. You take these ball states, and then you start with a trial function for the Vernier, and you start projecting these states in this Vernier function, and then you start changing the Vernier function to get this maximal localization of the Vernier function. This is what people have been doing, and when I moved back to Brazil, I had the one job that was getting these Vernier-like Hamiltonians for some very complicated systems. Multi-layer of magnetic materials and non-collinear, and I suffered for several months and I couldn't do the convergence. Because sometimes the convergence of these Vernier functions is very difficult. So the plane waves are very, there are several advantages, but what we would like to do is going from the left picture to the right picture. Again, most people have been doing this using Vernier functions. We are going to propose a little bit different here in this next few slides, okay? So what we are going to do in this part is we're going to do the following. We are going to take these constant orbitals from the DFT calculation. Okay.
Sorry. So you made a comment that in going to this one-year basis, you try to maximally localize the one-year functions.
Yeah, it's not necessary in principle. I think they implemented a version that you can just do it a direct projection. But in general, people do the maximum localization because then the extension of your hopping is going to be smaller. For example, you have like 3 neighbors hopping is already enough to describe your material. Okay.
But in principle, I always had this issue, right? That if you're writing things in a gauge, not in a gauge invariant way, it's somewhat problematic, right?
Yes, that's another problem of the Vernier functions, because if you not the Vernier functions itself. Let me change this statement. When you do the Vernierization process, for example, you can start. For example, you have these sites on your material, and you put like atomic orbitals in each site. During the Vernierization process, for some reason, if the symmetry allows, this orbital is going to move out from the site to the middle of the bond, because there is where you are going to get the maximum localization. This can be a problem depending on the calculation that you want to do it. That's what you mentioned. Or?
Yeah, in some sense, yeah. So I guess if you have your one-year state that with its center in between, that's a topological term. That's a very phase calculation, right?
Not necessarily. For example, if you take the silicon, and you are going to do a Vernier 90 calculation, you can just start guessing a orbital that's going to be in the middle of the bond, because there is going to be, how can I say, if you don't, the system is going to move into that direction. The convergence is going to be very badly. But when you start, when you know your chemistry, you can, how can I say, guess it already where it's going to be.
Yeah, but so I agree with that. I still think that's the very phase term, which is the center of the one-year function. But then the shape of the one-year function is gauge dependent. Is that, and that's what you're trying to minimize, right? The localization.
Yeah, when you do the localization, you want to minimize the shape so you can have, how can I say, because if you have a very localized base, these hoppings terms are going to be much smaller than the, of course, you cannot have a super localized, otherwise you cannot describe your system. So you try to have this compromise between. Okay.
Sorry.
Why did you say that?
It's gauged. It's not gauge invariant. Okay. Yeah. Sorry. That the center is
okay, gauge invariant
modulo a unit cell.
Okay.
But that is shape.
in our case, we have no how can I say, we don't play with the shape. We have an atomic orbital centered in a site, and you're just going to perform a projection on that site. Okay. So, and then what kind of atomic orbital? That's another thing. When you run the DFT calculations inside the pseudo-potential, there is already atomic orbital that we call the pseudo-atomic orbital that was used to construct the pseudo-potential. So this is the one that we're going to use it. And then we are going to simply expand the Conshan wave function in terms of this atomic basis. And to do that, you just need to perform this projection here of the plane waves on top of this localized basis. It's a very simple procedure. We do that when you calculate the density, projected density of states. What we are doing is basically this one here. So you already have, I'm going to show a pipeline of this. You already have something very similar to that. And but anyway, when you do this directly without thinking, you do this projection directly, what you end up is this kind of band structure. This is histidine. It's a 2D material. It's even topological, but this calculation is without spin of the coupling, so there will be no gap. When you do this, what you end up is the following. You see that these parts of the band structure are very well described, you know, but then you have these strange null values here for the eigenvalues. And the reason for this strange zero value eigenvalues is the following. That now I have a simple SPD orbitals to describe this whole band structure. So it's very hard that I will be able to describe these high energy bands in terms of this SPD. Probably the orbital character of those bands are much different than this SPD that I have here. Of course, this, I don't know if it's 5S, whatever. But, and then when you have this direct projection, we end up with this strange thing here. What is being done in this paper here is a way to filter out these states that are not physical, and I'm not interested in them, and I want to remove them from my region of interest. So what we do is this projectability operator. We have this projectability number that we can calculate for each band, and the interpretation is quite simple. If Pn is close to 1, I say that that band can be well represented by my basis. If Pn is lower, much lower than 1, this state is going to produce null eigenvalues, as I showed before. So if Pn is close to 1, these states will have all Pn very close to 1, these ones here. And then probably these guys here in this above 2 EV are going to have these projectability numbers very low. And the idea is to simply shift these states that have low projectability, okay? So now we take this operator, and then every state that has low projectability, I move out of the window of interest, okay?
What do you mean that every state that has low projectability, take it out? What is the meaning of this sentence?
Sorry, can you repeat?
The one you just said. Low projectability states.
I just shift them out of the. I can put how can I say an on-site energy on these states that are going to be out of the how can I say from -10 to 2 eV here.
So you have your states of the Hamiltonian, and then you want to put another operator, and then you want to divide them into the ones that you can detect something and take away the zeros. Nevertheless, could be mixed in the states because they don't commute these operators.
No, yeah, you're right, but it's like we can just take identify the states that cannot be represented by these small bases, and I can just, how can I say, sum a term that's going to shift them out of the window. But you are right, maybe you can have like, how can I say, interactions of these states with the other ones. I think this can happen. But
very small places.
Probably, if you go, for example, if you take this band here, you see that they are very well described. But there is how can I say, there is a difference between the pure DFT and our approach. It's a small difference, but it's there, you know. So depending on the system, I cannot even reproduce the valence bands well. So and then what I have to do is go back here and increase my orbital space to get to the correct representation. Okay.
If you were to draw the eigenvalues of the orbital, the projection of the orbital.
What do you mean draw?
Well, there is draw. How are you choosing? You're choosing because you have some eigenvalues of something.
How am I choosing the ones that I'm shifting?
Yeah.
No, I just look for this. You see here. Here is this projectability number as a function of the Fermi energy. You see, the low states here that are these guys around this region in energy, they have a very good projectability. You know, 1 close to 1. And then when I reach this region, these high energy states are completely crap. I cannot describe them decently. So what I do is that I decided, like in general, we use like 0.95, that projectability number. And then everything else we shift it out of the window. And then the message is the following. This is very good as long as I keep below this energy here. If I want to say anything above this energy, I cannot do it. Either you go do something else or you can increase your basis and then increase this level here. Okay? So, in this,
excuse me, sorry, and these projectors are built from the orbital character of each band that you're going to probe.
Yes. For in the DFT, I don't know a priori what's the character of the bands, but I projected on the orbital sites, on the orbitals in the site, and then I got how can I say, projectability number for that band. Okay. And then with this approach here, for example, for the Easternin, if you go to the DFT, you would have like 10,000s of plane waves that would have to perform this sum over these bands here. But now I have 9 orbitals per site. Since I have 2 sites, I have 18 orbitals that I can run these calculations. And now I switch from a very computational demanding problem to a very easy problem to solve. I can solve in my notebook. Okay? So that was okay. Now this is the code that we wrote. And then in PowerFlow we can do a lot of things. You know, band structure, frame surface. Another mentioning that's very hard to find the value points. We have also some structure to try to find the value points because the splitting sometimes is so small. And to do that, you need to interpolate in K points. So since we have such a small basis, interpolating K points for us is very easy. And we can calculate topological invariants, spin, orbital, anomalous Hall conductivity. And then I put these 3 last here in red because they are the newest ones. And also because they are being done with codes outside PowerFlow. I exported my Hamiltonian from PowerFlow, and then I give it to these guys, and then they run this calculation. I'm going to show just 2 of them very easy, not these ones, but these 2. We can do, okay, and then PowerFlow is very easy to use it, because it's like you can go to Python, do a pip, and then you install it. Somebody downloaded the PowerFlow, published a physical review letter, never contacted us, so very easy to use it. Yeah, he cited it, but they never contacted us. So it's very easy to use it. And then just to, okay, this is the pipeline that we do it. I take up material from the C2DB, I do structural optimization with Ponte Espresso, take my projections, and then construct my Hamiltonian. How can I say, I look for my projections. If it's above a threshold, I accept that band. If in some cases, I cannot find any band that's above this threshold. So then I have to go back and change my pseudo potential or do something else. Okay?
Sorry, this threshold is in some particular energy windows? Or you...
No, the threshold is the following. If your band doesn't have how can I say, a projectability that's larger than 0.95, you shift it. You know?
Send it up.
Yeah, you shift it to higher energies. There is also a way to so that's the full. Sometimes you can lower this one, but never below 0.9. Never below 0.9, because otherwise the orbital character of your band might be wrong. And that's important, you know. So you have to be careful. And then I construct my Hamiltonian, and I can do whatever I like.
All these bands are going to be degenerate all over the place. What does it mean to shift a
that
band?
Those
but they're all crossing, and then. How do you move a band that is all crossing all over the place?
No. You mean this? Okay.
Yeah, in this one they look very nice, but you have a whole of bands crossing.
No, but if it is whole of bands, have a good projectability, I'm not going to touch them. I'm just going to touch the bands that I cannot represent in these small bases. Of course, there are some cases that, for example, I can give you an example. There are some cases that I cannot even reproduce the valence band. So in that case, I can do anything with that Hamiltonian. I have to throw away, for example, we have a paper on phosphorine. Phosphorine, I cannot represent, I don't know, because phosphorine has a 1 EV gap. I can represent the valence band, but not the conduction bands. So what we did is, that I didn't mention here, instead of using these pseudo-atomic orbitals that come in the pseudo-potential, we have internal bases now. I have atomic orbitals that I can choose, okay, S, P, D, and then 5S, we can increase the band. And then that's what we did for phosphorine, because phosphorine, I couldn't reproduce not even the first band in the conduction bands. So then we have these internal bases now that we can do it. But I only use the internal bases if I have to, otherwise I use the pseudo-atomic orbitals. And all of the calculations that I'm showing here, I use the pseudo-atomic orbitals. And okay, so just to finish my advertisement here, we did the topological insulators, and this is important because these are very large supercells, 400 atoms, and we can put the spin-orbital coupling in a posteriori, so it's computationally very efficient. And also we can do this linear response spin dynamics where I have my Hamiltonian, and this part comes directly from Paul flow, and this part I can fit it from Paul flow to get the spin-orbital coupling parameter. This is a Zeeman field, and this is my Hubbard parameter. And now with this Hamiltonian, I can solve the equation of motions for this problem, and I can get the Magnum spectrum. I can get the response to because here I'm applying a Zeeman field, but also I'm applying a AC field in the plane.
So Marcio, you calculate just the non-spin-orbital coupling case, and on top of that, you start to put the Hubbard and put spin-orbital coupling, Zeeman.
Yeah, so far it's for these problems here, we have a technical problem that I cannot do it with the spin-orbital coupling from quantum espresso. But this is just something that I'm going to solve at some point. Because when I do the spin-orbital coupling quantum espresso, these hoppings here, they come in the total angular momentum basis, L plus S. And we had two options. Either we make a transformation from these hoppings to the spherical harmonic basis, or we rewrite this term here in this J basis. And I told Antonio, I'm not going to do it this one. He said, I'm not going to do it this one. So far we are doing without spin-orbital coupling, and we are putting the spin-orbital coupling by hand, which is fine. It's not perfect, but the band structure looks very, very, very good comparing to the DFT. Okay, but this is something that we are going to solve, and at some point, the only parameter that we're going to have for this spin dynamics is going to be the Hubbard term. That's easy to use. We can, in general, we put the value of Hubbard, the U, to obtain the magnetic moment from the DFT calculation. So it's a parameter, but it's not because people sometimes play with these parameters like crazy. No, we put the U to reproduce the magnetic moment of the DFT calculation. Okay, but we are going to solve this one at some point. And then we get this nice Magnum spectra. And also we can do the spin dynamics instead of the linear response. The linear response is very good, but still very computational demanding. Now we're implementing this atomistic spin dynamics where we can calculate the GIJs, the DIJs directly from these DFT calculations. And this is the equations. I'm not going into much detail. And then with this one, now I can solve this Hamiltonian, and then we get the dynamics for these materials. We can see non-collinearity. We can see even depending on the case, some phase transitions for this. Okay. So now ends my part of the advertisement, because this is important, because now I'm going to run several hundred DFT calculations, and I want to compute the spin Hall conductivity. Again, remember, I wanted to do a classification for quantum spin Hall insulator, but Tixen.
For the part that I just talked about, for the Zeeman energy, how do you determine the G? Does it depend on which band you?
Yeah, no, you're right. Probably I shouldn't. This is just a Zeeman field that we put to drive the system in the magnetization in a given direction that you like. We are not very much, how can I say, worried with the G in this case. Okay. So, and then what I wanted to do is to have this topological classification, but we had this paper that already did. So, and then we came up with an idea that was the following. Okay, we know from this paper, from the Professor Kane paper, that he mentions the relationship between the spin Hall conductivity and the quantity spin Hall insulator should be quantized. We also know that that's not the case in general because you have interactions that is going to break this quantization. From all the calculations that I did, what I found is the following: that if you have a very tiny gap, this spin Hall conductivity is not going to be quantized. But for the large gap ones, in general, I'd say that most of the ones that I did for 2D materials, they are quantized. So there is something here that's not only the spin of the coupling, but depending on the size of the gap, you're going to have or not quantization. So we knew that the quantity spin Hall insulator had this quantized spin Hall conductivity. And then, well, this is just a typical example. This is a quantity spin Hall insulator, and then this is topological gap, and then this is the spin Hall conductivity that's very close to 1. What's interesting also that we have a pseudo gap here in this region that's also topological, this one. You see, it's a little bit above 1. I cannot understand that very well, but it's... So this is a typical response for the spin Hall conductivity for a quantity spin Hall insulator, okay? And so now we change it up.
Just curious, when you say the quantum spin Hall is not quantized, you mean what calculation are you doing? What's the quantity that's not?
It's the spin Hall conductivity. For example, if you take I think it was shown here in some talk. Take germanium, you know, there's a tiny gap. And you show these values not 1. It's a little bit lower than 1.
Yeah, I see. But this is all numerics, right? Like
Numerics, yeah.
And but it's not a simulation of some transport or something like that.
Okay, no, I understand. If, for example, if I cut nanoribbon and then I do Landau calculation, I should have quantized the.
Because my understanding is that from the point of view of the bulk, if you calculate invariant, the invariant is quantized.
Yes.
What's not quantized is the transport on the edges, right? Because you can mix the spin sectors.
Yeah, that's true. If you, for example, even for the germanium that has this not quantized spin Hall conductivity, Z2 is equals 1. You're right. It's like a.
So I'm curious when you say it's not quantized. This is all a calculation on the bulk of the material. What is it? What's the thing that's not being quantized?
I mean, why is it quantized, not quantized? It's not an invariant of any kind.
The topological invariant is quantized, right?
The topological, but this calculation is not the topological invariant.
That's what I'm asking. What?
That's a transport calculation.
It is a transport.
I apply a field in a given direction. I see the response to that field. Okay. So because that was a big discussion. For example, in that paper that I showed here, we see that these values should be 1, and then for several materials they are not, because there are some interactions of the, as I said, that you are going to mix the spin up, spin down, and then you're going to break this.
Yeah, no, I agree. It was just not clear to me what is it that's here.
Okay, no problem. So then what we did is the following. Now that you have the topological classification of the database, we are going to eliminate all topological insulators, quantity spin Hall insulators. We are going to eliminate all the crystalline insulators also, because I know they are topological materials. And I'm going to run the spin Hall conductivity calculations for everybody else. Okay? So because I want to see if there is any of these 693 materials that are not quantity spin Hall insulator, are not topological crystalline insulators, but they have a finite spin Hall conductivity. It's kind of how can I say, desperate attempt to find something. That's true. But of course, we are already with the implementation ready, fully parallelized. Let's do it. Everything was calculated already. So that's what we did. And then what we found is the following. Most of these 700 materials have 0 spin Hall conductivity, as we expected. But there are 7 candidates here that they are not topological crystallines, are not quantity spin Hall insulators, but they have something here in the spin Hall conductivity sector. And as I mentioned in the first day, we are kind of, okay, what's that? And then we guessed, okay, maybe this is a higher order topological insulator. And with this guess, I'm going to say what's a higher order topological insulator. With this guess, we went in two ways. I went to exploring a tight binding model just for higher order topological insulators, and one of our collaborators went to explore to calculate the indicator, the symmetry indicator, okay? So before going to that, the higher order topological insulator was proposed, I don't know, 2018, I think. And the idea is the following. The high order comes from the following. If you have a 3D material, for example, topological insulator, and you have a bulky bismuth selenide, bismuth 2 selenium 3, and then you cut a surface, what you're going to see is the classical surface states, the direct cone and all of that. And that's in 3 minus 1. In the 2 dimension, you're going to see it. But for the higher order topological insulator, you need to go lower in the dimension. So for the bulk system, to see these topological states, you have to go, instead of a 2D dimension, you have to go to 1D. You have to build a wire of this material. And another thing is that the conducting states, in this case, they are not going to be in the surface or whatever. They're going to be in the hinges of this material. So it's going to be along these directions here. So this was done for the bismuth, and this is the bench structure, let's say, along this direction. Then you see that you have these hinge modes that are transporting, if you apply an electron field along these directions here. Okay. In our case, it's going to be a little bit different because you have 2D materials, and then instead of for a quantum spin Hall insulator, you take the bulk and then you build a nanoribbon. It's going to show the direct cones in the edges. But here we have to go to the lower dimension so we can see here. This is a nanoribbon along the zigzag direction. I have a gap at the spectrum, and this is a nanoribbon along the armature direction. I also have a gap spectrum. But then when I go to the 0 dimension, that's a nanoflake like this, I see these corner charges that are located in the corners, of course, of the material. Okay? So this is the higher order topological insulator. And then what we started, if you go to the original paper, the Science Advanced that I showed, they had a model, a type binding model for a higher order topological insulator, but it's different from ours. This is a quadratic lattice. And then if you remove this term here that they call mixing term, what you have is a 2D topological insulator, quantum spin Hall insulator. And then if you calculate the bench structure and the spin Hall conductivity, you have the one that we expected. And then you do the nanoribbon, you get the edge states. And when you go to the 0D, also you have these edge states around the system, okay? But now I'm going to turn on this delta. This delta here, when it's non-zero, drives the system into the high order topological phase. So that's what I did. Now we turn on this delta, and you see what happens. The bench structure is a little bit different, and now my spin Hall conductivity is smaller than 1, exactly in the case that I have been seeing from my materials. And then I can go to the 1D. I have a gap in the spectrum, and for the 0D now I have these 8 degenerated modes in the Fermi level. And when I plot the spatial localization, I see exactly they are located in the corners of this material. Okay, so again, this is we saw something from the DFT calculations. Now I took a model for the high order topological that is consistent in what we have been seeing. To finish the case, okay, this is just we're exploring the models that we see there is a competition between the spin optocoupling and this delta parameter, because we are puzzled by the following. Why some of these guys has 0.3 for the spin Hall conductivity and others has 0.8? We believe there is something to do with what we're seeing here in the model, but it's very hard to connect what this delta means in the model to what this would mean in a real material. This is something that we couldn't do it, because what we are showing here that if you increase this delta value, the spin Hall, how can I say, go to lower and lower values. I have So this is a completely variation of the parameters. And then you see delta 0, we have just a quantum spin Hall insulator and a normal insulator. And then in this region here, everything above this line is a higher order topological insulator. But anyway, the spin Hall conductivity is going to be very small. Okay.
So this delta is not the spin-orbit coupling interaction?
The delta, no. The delta is this term here that drives the system into the higher order topological phase. It's going to be responsible for gapping this.
But is the mixing the up and down states?
No, it's going to mix up and down states, but the spin of the coupling is this one that's an imaginary part, that there is an imaginary number here. So this is the spin of the coupling term. Okay?
How did you calculate before the C2 invariant?
Before?
Yeah.
For
this one. Why does it, how do you do the calculation for C2 invariant?
In the model?
In this one. Because somehow...
I didn't do the calculation for the Z2 invariant. I think you just...
But you just said that you took it out from the list because the C2 was on your pipeline and you took the...
No, but the model is a different thing. I mean, you mean the materials?
Yeah, exactly. And the material is not there. Then you're trying to model. And then somehow it looks like this is a topological insulator.
No. What I did is the following. First, I started without this this term here. And this is a topological insulator. But I never bothered to calculate the Z2 for this part, because I know that it's going to be, how can I say, this is a known model for topological insulators, but I didn't calculate the Z2 for this one. But in principle, we could calculate this one.
Yeah, I'm thinking that means that you have some Chern class and some opposite Chern class of 1, but then if it goes to the other case, that means it has to spring, to jump to 2, because otherwise it would be a topological insulator. 1 or. Well, for the spin Chern class.
Okay.
Since you have a gap, you can calculate the spin up, spin down.
I could calculate it here. If I calculate it, it would be Z2 equals 1 here, for sure.
In all the cases?
No, not in all the cases. When I go to this case, it's not going to, Z2 is going to be 0 for this one.
So then some Chern class jumped.
There is a...
to 2 or to 4 or to something like that.
Okay, yeah.
I see.
Yeah.
Well, but what is awkward is that this jump should be seen also in the spin anomalous Hall conductor. But you don't see it, it's very similar. The jump in the Chern class.
I understand what you're saying. You say that this is basically continuous.
It should jump to 2. But this is what I'm thinking in my head, because if it stays on 1, somehow the Chern class was 1.
Okay.
Otherwise, there is no change phase. So, but don't worry, keep it.
Okay.
We talk later.
So the term that you add to cap out the edge states must break time reversal symmetry.
No, it doesn't break time reversal. That was the thing, because in the original, I didn't mention correctly. For the original model, it came from this.
Sorry, but how are you breaking Kramer's degeneracy on the edge states then?
I understand what you're saying, because for example, this is an 8-band model that we took from. Because I remember we had this discussion that we should have because our materials doesn't break time reversal symmetry. They are all non-magnetic. So I could not have the model that breaks time reversal symmetry.
Okay, but then so let me ask something then. How many bands do you have below the gap?
It's these are 4 bands degenerated here and 4 bands on the top.
Okay. I see. So that's fine, right? Because if you had only 2, then you have this protected point by time reversal.
That's true. That's true.
And then what happens is the moment you break time reversal symmetry, you gap them out, and then you cannot assign the C2 invariant because you're not preserving time reversal symmetry.
That's true.
But what you're left with is with the corner states. The corner states that's then a high order.
That's true, because at the time when we were searching for the model in the original paper of the high order is a model that breaks time reversal symmetry. But we didn't want that, so we go to these 8-band models to avoid this that you mentioned. Okay, so now I explored this, and then we went to this to classify the material. And we took this, how can I say, the route that the route that these guys did for we calculate the eigenvalues of the C3, because all of these materials that I'm going to show, they have the C3 rotational symmetry. And then, okay, this is one of the materials has a 0.5 spin Hall conductivity. And then when you calculate the values of the C3, the eigenvalues of the C3 rotational symmetry operator, what we get is that this guy is a higher order topological insulator. We get the -1. So showing that these guys are higher order topological insulator now from the invariant that you should calculate. Okay, so with this one, when you submitted the paper, of course we tried first physical review letters, we passed the editor, but the peer review was not favorable for us, and then we changed it. Okay, before telling the story, that just finished, and now I create a nanoflake of this material. And then when I projected these 6 red states, I see the corner charges exactly where they should be, okay? So, and then I have some other materials that are going to be also high order topological insulators. All of them, they have the C3 rotational symmetry, okay? And at the time, this was the first paper that could find several high order topological insulators. Of course, after this came these automatic calculations, and then we were out of business with this approach. But and then, okay, so after all of this filtering and calculating, we find these 7 materials, and just to during the peer review process, not for the computational materials, but for the physical review letters, they asked, okay, can you see this for 3D materials? And then we went to archive, and then we found this paper here. By they predicting the paper that this bismuth bromine is going to be a higher order topological insulator. We calculate the spin Hall conductivity, and then but for the PRL, we didn't have this one. Maybe we could turn the tables if I don't know. But then we managed to. So my guess is like, I'm going to finish the story. So, and then there is another paper also that came that predicts also this guy's topological insulator. And it has a non-zero spin Hall conductivity, but it has a Z2 equals 0 for this one. So just to pass a little bit fast here. So I did all these things for the spin Hall conductivity, and then I got lucky because I got the position, the university where I am. And then Professor Bechar and Tatiana is in Portugal, but they are doing a lot of things in this orbital Hall. And then they asked me, can you implement the orbital Hall calculation? I said, I can. So pandemic starts, I'm sitting at home, but I say I'm going to do very fast. But I have an 8-year-old daughter, at the time was 4. So it was very difficult, but then we managed to implement because there are, the implementation is simple, but there are a lot of technical problems to build this matrix here, but it's fine. And then the first paper that we did was the following, because now the orbital Hall is getting some momentum, but there is a big problem with it. How to identify univocally the orbital Hall effect. Because if you go to the original paper where they did the spin Hall effect, you have this spin accumulation on the sides of your sample. But when you do valley Hall effect, you're going to have a spin accumulation on the sides of their sample. When you do the orbital Hall effect, we are going to expect spin accumulation on the sides of the sample. So how can you separate these 3? So which one is contributing? So what we proposed was the following. We knew at the time that the molybdenum disulfide H phase 1 layer has a 0 spin Hall conductivity, basically, and has a very large orbital Hall conductivity. But nevertheless, this guy here breaks, it doesn't have inversion symmetry. So I have also the valley Hall effect in this one. So what we proposed has a non-zero valley Hall effect. What we proposed at the time, instead of doing 1 layer, let's put a bilayer in a correct arrangement, so we can kill the valley Hall effect, but maintaining the spin Hall, the orbital Hall, and the spin Hall is going to be 0 anyway. So that was our proposal, and we're lucky that so has inversion symmetry, valley Hall should be 0, and the only thing that you are going to detect from this one is going to be orbital Hall effect. And this one we got lucky. People from PRL liked it, and of course. We had a lot of problems to pass it because how we are going to build this, and we say, okay, we are not experimentalists. I don't care. They should try it. So we had this, but in the end we managed to do it, and then, of course, now there's better proposals than ours. So we're lucky that we did this in 2021, because now the experimentals are jumping to the orbital hall, and then much better approach, because this is a very difficult case. You have to put them correctly arrangement, and then you have to do the measurement. Now there is much better proposal than ours originally. And just to finish everything, after we published this in 2021, and then these two papers came out showing that the molybdenum disulfide is a high order topological insulator. But the molybdenum disulfide has a 0 spin orbital hall conductivity. So first thing I thought was like, oh man, my paper is wrong. And then I got this panic for some days, and what we realized is our criteria of this spin hall conductivity is not complete one. If the material has non-zero spin hall conductivity, we believe that it's going to be a higher order topological insulator. But it doesn't say that if it's 0, it's not going to be a high order. So this guy showed that, and then you see here I have a 0 spin hall conductivity, but I have a finite value for the orbital hall. And then we managed again to, in this paper here, I'm not going to pass very fast this paper. What we did here is something similar, but instead of looking for the spin hall, we are now playing with the orbital hall conductivities. And all of the high order topological insulators that we had here, they have a sizable non-value for the spin hall, for the orbital hall conductivity. And then we have a kind of a model to explain why we should have this one. And just to finish this, okay, after doing all of these calculations, now I have this large database of orbital hall conductivities and spin hall conductivities, and we are doing some machine learning so we can predict the orbital hall without having to run the calculations. This is still in the early stages. But and what we are going to do also to run these calculations, we have the Hamiltonians for all these 2D materials. At some point, we are going to put in a public database so people can use it also. Since we how can I say, we benefit so much from the database of the Professor Tigson, we want to give something back also with our Hamiltonian. So with that, I finish here. I thank you the supporters, and thank you all for listening to me.